Hi everybody, this is the second lecture on error analysis from Chapter 3 of the Engineering Surveying textbook. We talked about some of these concepts in the last lectures, and today we're going to do the execution of the equations, and I'll show you how to use them, how to find all of the data that you need, and how to do your homework. Then I will do a homework problem number 3.6 for you so that you'll have an example in your notes. So the first thing that I would like to make a clarification on, the term error is used differently than the term mistakes in surveying. A mistake is a blunder or something that you have done incorrectly. An error, on the other hand, is just part of the process of measurement. No measurement, unless it's a counting number, can ever be exactly precisely 100% correct. It's always dependent upon the instrument that you use and some other factors as well. But if you think about it, like we talked about in our, when we were using the Philadelphia rod, that the Philadelphia rod is graded to hundredths of a foot. So you can read whether a measurement is 100th or 200ths or possibly halfway in between. But there's no way that you could take that out to 4 decimal places. So there is some built-in error in that measurement that is separate from the idea of a mistake. So what we're doing with this idea is if we have a length, for example, that we want to measure, and we want to know how long, what is the distance between 2 chaining pins. What we're really talking about is what is the most probable value. Now, that seems odd when you think about a measurement, but basically this is saying what's the most likely number that this measurement is. And sometimes to do that you will take repeated measurement. So this formula, which says m bar is equal to sigma m divided by n. Mathematically, this means m bar, the average value or the most probable value, is equal to the summation of the individual measurements, in other words, all the measurements that you took added up, divided by the number of measurements you took. And after we find that average or that most probable value, we take, if you took any individual measurement and subtracted it from that average, that difference would be the residual. And then the next thing that we find, this has to do with the relative spread of that data. In other words, if the normal distribution is quite steep or quite broad, this is referred to as the standard deviation. And the standard deviation is plus or minus the square root of the residual squared summed up, divided by the number of data points you took minus 1. So you take the square root of that entire thing, which I'll show you in the second part of this lecture. But as we discussed last time, if you go 1 standard deviation below or above the mean, you will capture 68.27% of the data if it's normally distributed. 2 standard deviations above and below captures 95% of the data, and 3 standard deviations above and below captures 99.7 or nearly all of the data. So then we talk about the probability of error. Now, if you've ever answered or if you've ever looked at like a political poll, sometimes they will say things like candidate A will get 52% of the vote plus or minus 6%. And if you ever think about data like that, it's strange because if candidate A gets 6% less than that, they would lose or could lose. And if they got 6% more than that, then they would win. But that's the way that it's written because what we're really saying is we really don't know for sure until election day. So the probability of error, E sub p, is equal to some constant times that standard deviation. So once again, we always have to find the standard deviation before we can do any of this other work. But the E50, or what's called the probable error, is 0.6745 times the standard deviation. That means that if you take the standard deviation and multiply it by 0.6745 and take that range above and below the mean, that you'll have 50% of your data, or it means that you're 50% likely that the value that you've chosen is correct. E90 means that you're 90% confident or convinced that your data is correct, and E95 means that you're 95% convinced that your data is correct or that your value is correct. And E95 is used a lot in the social sciences. Like if you're talking about what is the likelihood that using reading program A will improve a student's reading ability, you would take a bunch of data from a bunch of students who had reading program A and from students who had a different reading program, tabulate it all up, come up with a standard deviation, and multiply that by 1.9599, and then that range would say between here and here, I am 95% confident that I have identified whether this is better, worse, or whatever your criteria is. The next piece of the next calculation we do is the standard deviation of the mean. Once again, it's based on the standard deviation plus or minus the standard deviation divided by the square root of the number of data points. And what that means is this is the range within which the measurement has a 68% chance of being above and below the mean. So you're 68% likely that the value that you've chosen is within that 68% range based upon that. Now, the last thing that your textbook talks about, and the last thing I'll talk about before I show you how to do this kind of a calculation, is the least squares adjustment. And what this means is a least squares adjustment is something that you would do using a surveying package. You can do these by hand, but they're very time consuming. So, and they're very, very easy to do with application software. But what a least squares adjustment does is takes data points, finds a line that best fits the graphed data points by taking the amounts above and below the residuals, essentially squared, and adjusts so that those are equal above and below. So this is a process or a field of study called linear regression. And there are a lot of different things that are solved by least squares adjustment or linear regression. But this is just one way to say I'm going to converge on the most probable value and evaluate whether my answer is most likely the correct answer. So that's all what we're getting at, is trying to describe this data set. So having said that, I have a problem worked out for you. I worked out problem 3.6, and this is a problem that you will have for your homework. Hang on, I'm trying to drag it over here. And also, this would be I went off camera a little bit. You may have noticed a splice because I wanted to find this problem and I didn't want to waste screen time digging around for it. But this is problem 3.6, and basically what we find, we're given a data set in 3.6, which are 10 measurements of the length of a line, and these are measured in meters. So as you should expect, those distances are close to each other. In other words, if you measure the distance of a line 10 times, you expect all 10 of those values to be fairly similar. If you have one that is excruciatingly different, like we have a bunch that are 65.396, 65.401, if we had a measurement that was, for example, 56 point something, we would probably recognize that as a bad data point. And it was probably because the person who wrote them down had flipped the numbers. But there's a bunch of different reasons why you could have a bad data point. But those are called outliers. And generally speaking, you want to just eliminate them from your data set. But to execute this problem, which is to find the most probable value of the length of that line, the standard deviation, and the standard deviation of the mean, we go through this process. The first thing we do is we write columns of data, and we start by writing all 10 of these data points, all 10 of the measurements of that line, and we add them up. So you notice over here, the symbol says summation m. That means or sigma m, which means summation or add up all of those data points. Then we know that to find the average value, m bar, we take the summation of m and divide it by n, the number of data points, which is 10. So we take the summation of those numbers in that column, 654.102, divide it by the number of points, measurements, 10, and we come up with an m bar, or the most probable value, or the arithmetic average, of 65.4012 meters. That means that just based on averages, we would expect that the value of that line would actually be 65.4012 meters. Now, as you can see from these measurements, we're only measuring to thousandths, so we would really have to round this off to 65.401 based on the accuracy of our instrument. But we carry out decimal places until we get to the end of these problems, because otherwise we can build in a little bit of error just from rounding. So after we find the most probable value, 65.4012 meters, we then find the residuals, which are shown with an italicized V. V is also in meters, but in every case, if you remember from the last one, the last sheet that I had up, V is equal to, let's see if I can pull this up really quick. V, or the residual, is always equal to the most probable value minus m, which means the value that's on that line, each individual value. So if I have 10 data points, I will have 10 residuals. So this value, this residual, is the average 65.4012 minus this value, 65.401. This value for residual 0.0012 is once again equal to the most probable value, 65.4012 minus this value. So we do that 10 times. We find that residual, or that difference, 10 times. And you notice some of them are positive and some of them are negative. In other words, if this number, the individual value, is higher than the most probable value, the residual will be negative. So we have positive and negative residuals. If the measurement itself was exactly the same as the average, the residual would be 0. But what you see, and I just did this to make a point, if you add up all of the residuals, it comes out to be equal to 0. That is always the case. The difference between each individual value and the average, when you add them together, has to equal 0. So for computational purposes, instead of using the residual, we square the residual. So we take this number and multiply it by itself, or raise it to the second power. Now, in this case, because the residuals are small, the residuals squared are going to be extraordinarily tiny. But if you remember, a positive number times a positive number and a negative number times a negative number are both positive. So the residuals squared are always positive. So after we have written the individual values, found the most probable value, computed the residuals, then squared those residuals, we add up that column, the square of the residuals, and we come up with this value, which is shown by symbol summation V squared equals. So this number, 0.000102, is the sum of all of the numbers here in my third column, the residuals that have each been individually squared. This is not the same as adding them up and squaring it, because that, of course, would be 0 as well. All right, after we've done that, we have everything that we need to find our standard deviation. The standard deviation is plus or minus the square root, the sum of the residuals squared, which is right here, divided by n minus 1. N is 10, so n minus 1 is 9. Summation of the residuals squared is 0.000102. And so when I do this computation, I find that that number is, let me stretch this out a little bit, plus or minus 0.0034 meters. So that means that my standard deviation is 0.0034 meters. Means if I go to my most probable value, 65.401 meters, and I subtract this number, and then add that number, that's the range in which 68% of my data is going to be captured. So then my standard deviation of the mean is the standard deviation divided by the square root of n, which is the square root of 10. And that number comes out to be plus or minus 0.0011 meter. That means that if I go this wee tiny little distance above and below the most probable value, that I feel 68% confident that I've actually determined the correct line length. All right, so that's it for chapter 3. I'll have these videos posted, and I will also have a homework assignment posted, which will be due at some date in the future. But once again, look for the word submit and submit by that date through Moodle, and we'll be good to go. You'll be all squared away. So thanks. We'll see you in lab.